I'll start. Thank you very much for giving me the opportunity. Just to give you an overview, our group's research broadly looking at, or we try to evaluate human impacts on natural systems, how it affects the land and water resources, and then how the changing weather patterns are affecting ecosystem services. By understanding these impacts, we are trying to develop solutions in order to improve land and water resources. If you look at the figure on the right, we all are part of the environment, the society in terms of how we operate, producing food, houses, population, dietary patterns, food security, all those aspects that affects the society is part of the environment within which we have different economic activities that appropriates a lot of resources, land and water and other critical resources. So they are all interconnected, which are impacted when they are repurposed or used for other activities. Now, when it comes to land and water resources and food security and the need for the environmental requirements, broadly, we are trying to answer two questions. Do we have enough land and water resources and human capacity to produce food for the growing population? And can we manage land and water resources sustainably for future generations? The views are diverse, depending on what you believe in or what the priorities are. However, we can all agree that water connects ecosystems across the landscape. Therefore, every action affects the ecosystem functions. We need to understand how these connections are made and how they in return impact various activities along the way as we impact the ecosystem functions. Here is a global assessment of water appropriation. This is around 2000, based on the assessment around the resource appropriation in year 2000. This was done by the International Water Management Institute, led by Dr. David Molden. The report was published in 2006. What you see here is, globally, we receive about 110,000 cubic kilometers of rainfall, which is all the resources that are available, and out of which how much is used for various ecosystem functions and services, including natural systems, crops, livestock, including rain-fed and irrigated agriculture, as well as industrial and domestic water demand. Now, I'm highlighting two different types of water here, green water and blue water. So green water is all the water that is available as soil moisture as a result of rain falling on the land surface. So most of the rain-fed agriculture, which produces bulk of our food globally, uses green water. And blue water is where we store either in groundwater reservoirs or surface reservoirs, streams and lakes, and then appropriate that for various other activities. So most of the time we appropriate majority of the majority of the blue water is used in irrigated agriculture. As you can see, 70% of the blue water withdrawals goes for irrigation, and then there is a very small amount that used by cities and industries. However, more than 90% of the appropriation goes back to the system as a return flow. So This vast amount of resources that we appropriate is significantly impacted by the changing weather patterns. So weather plays a key role in making sure how much is available, when, and where. Which is again in a big picture assessment presented here. As you can see, most of the South Asian region, there is significant amount of appropriation of blue water for irrigation or irrigated agriculture, particularly in most of the South Asian region, including India. In contrast, if you look at the African continent, it's majority green water. That is, there is less development in terms of appropriating water to increase production. So there is a disparity in terms of how much water is appropriated, how much food is produced, which affects regional food security. Now, in order to understand various drivers and how they affect our water food nexus, here I'm proposing a broader framework where we look at the issues through different, what we call lenses, right? For example, if you look at different goals for national regional food security, which we all emphasize heavily on, particularly in South Asian region. So that is one angle we want to look at in terms of how much water is available in order to satisfy all the domestic food demand. Another aspect is, environmental water needs. There are ecosystems that require certain amount of water during certain times of the year. So all those needs, as an environmentalist, one would look into how much water is needed for a certain regions, certain areas, or certain landscape types, right? And then there are also shared global and national goals, including international trade. So there are multiple competing factors that we need to take into consideration. Using that, we develop multiple solutions, try to maximize the positive benefits or impacts while minimizing the unintended consequences. I have listed several of those positive outcomes out of this solution space. Adequate water supplies, which is critical for our growing population, sustained and adequate food production so that the economic activities are sustained on the long term. And along the way, there are also, there can be unintended consequences such as increased drainage that can result in downstream floods or construction of dams that can prevent downstream flows, which may affect, in turn, the environmental requirements, right? So there is a compromise that we will have to adhere to in order to come up with a better solution that is acceptable by all parties. Now, going more narrowly into the water and food policy aspect of it, here I'm going to talk about a project that we started several years ago while I was working as a junior scientist at the International Water Management Institute, and expanding it to cover sub-Saharan Africa. The big picture idea that is shown here, we developed this water and food policy dialogue model, looking at these three major countries, China, India, and Pakistan, which currently account for nearly 40% of the global population. So it's critical that we understand and address the water and food security challenges in this region. And all three countries play a key role in international food trade as well. So what you see here in each of these charts that I'm showing, we are looking at around 2000 circa. What was the population, and then what is the typical calorie supply, or the demand for this population, based on which we estimate the food grain consumption, taking into consideration the diverse food that this region, people in this region consume. And then we also, based on the food consumption, we estimate the grain consumption that includes both food and feed, because there is also a lot of livestock raising for meat, as well as milk and eggs and other products, right? So what we did, we looked at these three countries for in the year 2000 or around 2000, and then tried to predict presently how much more we would need in order to meet the future or current day requirements, at the same time satisfying the environmental demands as well. So this is a big picture idea, but I'm going to narrow down to focusing on only in the Indian region, which is again, please note that this is still an ongoing work. We have been looking at various aspects, trying to put together a comprehensive assessment. So if there are questions that you have or suggestions, I will happily listen to you. Now, in order to estimate the food and the water demand, we've got to start with how much we consume. So the table on the left shows the major grain crops and then the per capita consumption in India. And the population pyramid in the middle shows the population distribution around 2000, both male and female, by age-wise. So we have this per capita consumption, based on which we can expand the analysis, which I will show how we expand it in a bit. Now, in order to account for the variabilities in weather, land availabilities, production, as well as various dietary patterns, and understand the spatial and temporal variability of available resources, we divided the country into 19 river basins, which are provided on the figure on the right. And then we conducted the analysis within each of those river basin units. How we extended the analysis from per capita grain consumption, using the population, we estimated the total grain demand by each of those crops, and then based on the available cultivated areas by each region, we estimated how much is being produced or how much can be produced in order to meet the demand. And then, in addition to the agricultural water demand, we also have the details, or managed to get the details from various sources, what are the water sources that are being used, whether it's groundwater, or surface water, or irrigated, or rainfed. Those details goes into this estimation. So that is on the agricultural water demand. In addition to that, we also accounted for domestic water demand based on average per capita water use for various activities, including bathing and use for other human demands. In addition to that, we also managed to get some information about industrial water use. As I mentioned earlier, we would agree with me that the domestic and industrial water demand, most of it goes back into the system as return flows. And then we also, based on some crude estimates, allocations for the environmental requirements, as well as the regional climate